Welcome to Introduction to Electrical Engineering. In this intro lecture, I'll show you an overview of the course so you know what's expected. In the first lecture of the course, I'll talk about what electrical engineering is. Here you'll learn all the subfields in electrical engineering such as control system or signal processing. From lecture 2 to lecture 4, we will look at resistors, capacitors, and inductors, and the basic electrical quantities, voltage, current, charge, and power. Here we will briefly explain how resistors, capacitors, and inductors behave in a DC circuit. In lecture 5 and 6, we will go into details on DC circuit analysis. Here you'll learn Kirchhoff current law, Kirchhoff voltage law, mesh and nodal analysis, as well as Thevenin equivalent circuits. A lot of examples will be used here to help you understand how to apply them. In lecture 7 and 8, we will move on to active circuit elements, diodes, transistors, and op-amps. Here you'll learn their characteristics and applications. Lecture 9 and 10 covers AC circuit analysis. It explains why complex numbers exist in AC circuits. Lecture 11 covers information on power generation, distribution, losses, and protection. Here you'll learn the basics of transformers and fuses. Lastly, in lecture 12, we will show you how to analyze real circuits and how to start designing your own one. Exercise will be given in these lectures, but I'll add more as we go. As you go through these lectures, you'll see that they follow one another, so I will recommend you to start from lecture 1 and work your way to lecture 12. Remember, the goal of this course is to teach you the fundamentals in electrical engineering in the most concise and efficient way. So I won't waste time talking about the history of electrical engineering or myself. I hope you enjoy the course and find it helpful. If you have any questions, feel free to contact me and I'll reply them as soon as possible. Thank you. Kirchhoff current law tells you that the sum of current flowing into a node equals to the sum of current flowing out of the same node. In this case, we have I1 and I2 flowing into node A, I3 and I4 flowing out of the same node A. So according to Kirchhoff current law, we know that I1 plus I2 equals to I3 plus I4. Kirchhoff voltage law tells you that the sum of all voltages around a loop is 0. To use Kirchhoff voltage law properly, we need to first determine the polarity of the resistors. The polarity of the resistors will depend on how you define the current flow. In this case, if we assume the current flows from the left to the right, like this, because we know that current flows from a higher potential to a lower potential, we will have plus here, negative here, from higher potential to a lower potential, plus here, minus here, plus here, and minus here. So now if we use Kirchhoff voltage law to the outermost loop, this one here, in the clockwise direction, like this, we will have plus Vs, because we go from negative to positive, we have plus Vs, and we go from positive to negative, we have minus V3 and minus V4 equals to 0. In the last 8 lectures, we learned how to analyze an op-amp circuit with resistors. We also learned the characteristic behavior of the inductors and capacitors. So today and in the next lecture, we're going to slowly guide you to be able to analyze an AC circuit with resistors, capacitors, and inductors. When we talk about AC circuit analysis, most people will just tell you that you need to use impedance instead of resistance. So the Ohm's law, V equals to IR, will just becomes V equals to IZ, where the impedance Z consists of a real number plus an imaginary number. Then they will start to talk about complex number analysis and phases. But what's important is that we need to understand why we use a complex number in the real world and what the imaginary part really represents. Since they are imaginary, do they actually exist? To answer these, let's revise how a capacitor works. Consider this circuit. When we close the first switch, the capacitor starts to charge and the energy is stored in the form of an electric field. If you choose to specialize in signal processing, you'll work with signals such as sound, image, video, music, or brain signal. The purpose of signal processing is to extract the most important information out of the signal using mathematical algorithms. A good example of signal processing is the lie detector that the police use. It first captures and stores a person's speech into an electronic device like a computer. Then it extracts the relevant features to determine the possibility of lying. Also, things like the eye scanners and cameras are a product of signal processing. Microelectronics involves the study of electronics at the microscopic level. So instead of dealing with electricity, they work with electrons and photons. And that's how our computers, laptops, and phones are getting smaller and faster. A lot of the new technology, such as the solid-state drive, is also a product of microelectronic engineering. Or you might have heard of quantum computing, and that's what they are working on right now. To begin with, you need to understand what electric potential and voltage are. Electric potential can be observed when you place a charged particle in the vicinity of an electric field. In this case, if we put two positive charges, one at point 1 and the other at point 2, they will experience different electric potentials, V1 and V2. And the difference in their electric potentials is known as the voltage V. The positive charge will move from higher potential to a lower potential, and how fast will this charge move depends on the voltage. Higher the voltage, larger the force will be to push the charge. So you can think of the voltage as a water pump and electricity as the water. Higher voltage means you exert more force to pump out the water. Note that there will be a voltage rise when you go across a power supply and a voltage drop when you go across a resistor. In an ideal case, voltage should be the same on the same branch of wires. In this case, the red wires should all be 5 volts and the green wires should all be 0 volts. Resistors are the most common electrical components. You'll see resistors in almost every circuit. A key feature of resistors is that it dissipates power and produces heat. We usually use letter R to represent resistors, and its resistance is measured in ohms. An ideal capacitor can store and release energy, but unlike a resistor, it does not dissipate power. The basic structure of a capacitor consists of two metal plates separated by a dielectric. A dielectric is simply an insulator that can store energy by becoming polarized. Based on what we use as the dielectric material, there are different types of capacitors. Ohm's law is one of the most fundamental equations in electrical engineering. It basically tells you the relationship between voltage and current for a resistor. According to Ohm's law, voltage across a resistor is equals to the current flowing through the resistor times the resistance. For example, if we have 5 volts across a 100 ohm resistor, we know the current flowing through that resistor will be 5 divided by 100, which is 0.05 amps. As for a capacitor, The current is equal to the change in voltage times the capacitance. Since a DC supply has a fixed voltage, the current flowing through that capacitor will be zero. In other words, the capacitor will look like an open circuit. Similarly, the voltage across the inductor is equal to the inductance times the change in current. Again, since the DC source supplies a constant current, the voltage across the inductor in this case will be zero, meaning the inductor will look like a short circuit. So if we have a circuit that looks like this with a DC supply, in a steady state, this is what it will look like. But how does this occur? Next, we're going to talk about another technique you can use to simplify a circuit. Thevenin equivalent circuit tells you that we can find an equivalent voltage in series with the equivalent resistance to represent any linear electrical network with some power source. The best way to learn how to find a Thevenin equivalent circuit is through an example. Assume we have a circuit like this, and we want to find the Thevenin equivalent circuit of this part. The first step is to find the open circuit voltage VOC. So we open up these two terminals and we want to find the voltage across it. If you look at this circuit, this is in fact a simple case of the voltage divider that we just talked about. So the voltage across R2 is just the total voltage Vs times R2 divided by R1 plus R2, which is 4 volt. Here's an example of using an NPN transistor as a dark activated switch. When the photoresistor is exposed to light, its resistance drops, causing most of the current to go from the supply through resistor R1 to the photoresistor. Only a very small fraction of current is flowing to the base of the transistor, which is not enough to turn on the transistor. Therefore, no current will flow through the collector-emitter junctions, and the LED will not light on. In the dark, the resistance of the photoresistor starts to increase dramatically, causing most of the current to flow to the base of the transistor, which turns on the transistor. As a result, the current will flow through the resistor R2 and LEDs to the collector-emitter junction, so the LEDs will now light on. Another commonly used applications for transistors is to use them as Darlington pair. To see how this circuit works, assume we start by inputting a voltage, say 3 volts at Vin. Initially, the voltage at V- is 0 volt, so the output voltage will take the difference between the two inputs and start to increase. As Vout increases, V- will also increase because no current flows into the negative terminal, so this part of the circuit will just look like a voltage divider, where V- equals to Rg over Rg plus Rf times Vout. Now, since V- has increased, the difference between the two inputs decrease. Therefore, Vout will decrease. Eventually, Vout will stop fluctuating, and we call this the steady state. At steady state, the output voltage Vout doesn't change, and therefore the two input voltages V plus and V minus are the same. In fact, we can use this conclusion to analyze any op-amp circuit with negative feedback. Welcome to Introduction to Electrical Engineering. In this first lecture, you'll learn what electrical engineering really is, what different fields there are within electrical engineering, and what electrical engineers do. So when we talk about electrical engineering, we know that it deals with electricity. In fact, it's the study of electricity and how we can use electricity for specific purpose in our daily life. For example, The electrical train that you take to go to work uses electricity to generate motion. The street light uses electricity to produce light. The washing machine uses electricity to wash your clothes. The speaker, the internet, and any device that uses electricity is a product of electrical engineering. Just to give you an idea of how broad electrical engineering has come so far, here's a list of different fields in electrical engineering. There are power system, signal processing, control system, microelectronic, telecommunication, and photonics. Usually, you'll get to choose one of these 6 fields to specialize in your final year of study, and now I'm gonna go through each of them. First of all, power, or sometimes called energy system, deals with power generation and distribution. How do you generate and deliver reliable energy to your client at the most cost-effective way is the main focus of power system engineering. For example, the power system engineer would have to figure out how to avoid system damage from a natural disaster like a thunder or an earthquake. Or when the system is already damaged, how can they recover it in the shortest period of time? If you choose to specialize in signal processing, you'll work with signals such as sound, image, video, music, or brain signal. The purpose of signal processing is to extract the most important information out of the signal using mathematical algorithms. A good example of signal processing is the lie detector that the police use. It first captures and stores a person's speech into an electronic device like a computer, then it extracts the relevant features to determine the possibility of lying. Also, things like the eye scanners and cameras are a product of signal processing. The goal of a control system is to provide a stable output. If you compare an old elevators with the new ones, you might find the new elevators more quiet and more subtle, but sometimes they can be a little bit too slow, and that's what the focus of control system engineering is, to be fast but stable. The control system basically takes into account of external disturbance such as the rain, the wind force, or even a human, and it will adjust itself to provide a stable output. For example, the temperature control air conditioning will take into account of the ambient temperature and adjust itself. And another example is the robotic vacuum cleaner. It will scan the surrounding and avoid obstacles. Microelectronics involves the study of electronics at the microscopic level. So instead of dealing with electricity, they work with electrons and photons. And that's how our computers, laptops, and phones are getting smaller and faster. A lot of the new technology, such as the solid-state drive, is also a product of microelectronic engineering. Or you might have heard of quantum computing, and that's what they are working on right now. Telecommunication deals with data transmission and reception. Just imagine billions of people are sending and receiving phone calls, videos, images across the world every minute. How these data are sent and received so reliably in such a short period of time is what telecommunication is all about. Lastly, photonics. Photonics involves the study of light. The most common example is the solar power panels that some households have. How to efficiently convert the solar power into electricity that we can use is what photonic engineers worked on. Also, things like the fiber optics, which use light to transmit data, are a result of photonic engineering. So that brings us to the next question. What do electrical engineers do? In each one of these fields, the engineers can be further assigned for different roles. For example, there are design engineers who do the initial design, project engineers who manage a particular project, system engineers who maintain and monitor all existing systems, and etc. In order for a particular project to be accomplished, all of these engineers have to focus on their role, finish the tasks, and pass on the result to other engineers. So, being an engineer, it is crucial to acquire the knowledge necessary for a particular job, apply it, and most importantly, they have to communicate with each other. So now, hopefully, you have a better understanding of what electrical engineering is, and whether you would like to learn more about it. Welcome back to Introduction to Electrical Engineering. Today we're going to talk about the most basic electrical components in a simple circuit: resistors, capacitors, inductors, and the power source. You'll also learn the usage of an ammeter and voltmeter in this lecture. Resistors are the most common electrical component. You'll see resistors in almost every circuit. A key feature of resistors is that it dissipates power and produces heat. We usually use letter R to represent resistors, and its resistance is measured in ohms. It's important to note that wires are not perfect conductors, and therefore they have a finite resistance, which sometimes plays an important role in a circuit analysis. An ideal capacitor can store and release energy, but unlike a resistor, it does not dissipate power. The basic structure of a capacitor consists of two metal plates separated by a dielectric. A dielectric is simply an insulator that can store energy by becoming polarized. Based on what we use as the dielectric material, there are different types of capacitors, such as ceramic, polyester, and electrolytic capacitors. Capacitors are measured in farads and are usually represented using letter C. An inductor is simply a wire winding into a coil, and since wires have finite resistance, an inductor also has some resistance and dissipates a little bit of power. Similar to a capacitor, an inductor stores and releases energy, and it's measured in henries. We often use letter L to represent an inductor in an electrical diagram. Lastly, to complete a circuit, you always have some energy source. The energy source can be from a battery, a generator, or a solar panel. Since the power consumption is different in different circuits, it's crucial to choose the right power supply for the circuit to operate properly. The important attribute of a circuit is its voltage and current. You'll learn the physical meanings of these two quantities in the next lecture. Right now, I just want you to know that to measure a voltage, you need to connect a voltmeter in parallel to the components that you wish to measure the voltage from. In this case, we are measuring a voltage across a resistor. As for the current, you'll need to connect an ammeter in series with the component you wish to measure the current from. In this case, we are measuring an overall current. We'll come back to this in lecture 12 when you have a chance to look at how a practical circuit is set up. Welcome back to Introduction to Electrical Engineering. In the last lecture, we talked about the most basic electrical components: resistors, inductors, and capacitors. We also talked about how to measure voltage and current. And today we will explain what voltage and current is. We will also introduce different types of power source. But first, why do we need to learn all this? If you look at the back of your laptop or any electronic device, you often see a little sticker that tells you what the required input voltage and currents are. It will also tell you what the power consumption is for this device. In this case, we have a HP laptop that takes 100 to 240 volts, 50 to 60 Hz AC supply, and it consumes 65 watts of power. So if you have a power supply like this for this laptop, it will not function. But why? Today you'll learn why you cannot connect your 240 volt supply to a 5 volt electric fan, but it is okay to connect your power supply to various devices that requires the same input voltage but different input current. To begin with, you need to understand what electric potential and voltage are. Electric potential can be observed when you place a charged particle in the vicinity of an electric field. In this case, if we put two positive charges, one at point 1 and the other at point 2, they will experience different electric potentials, V1 and V2. And the difference in their electric potentials is known as the voltage V. The positive charge will move from higher potential to a lower potential, and how fast will this charge move depends on the voltage. Higher the voltage, larger the force will be to push the charge. So you can think of the voltage as a water pump and electricity as the water. Higher voltage means you exert more force to pump out the water. Note that there will be a voltage rise when you go across a power supply and a voltage drop when you go across a resistor. In an ideal case, voltage should be the same on the same branch of wires. In this case, the red wires should all be 5 volts and the green wires should all be 0 volt. The electrical charge Q is directly related to current and is measured in coulomb. An electron has a fixed charge of 1.6 times 10 to the power minus 19 coulomb. So if we know how much charge there is, we basically know how many electrons there are. If we use the same water pump example, you can think of the electrical charge as the total amount of water in the water pump. The electric current I is defined as the flow of charge per second and is measured in amps. For instance, if you have a flow of 1 coulomb per second, that means you have a 1 amp current. Again, you can think of this as the speed at which the water flows in the water pump example. So if we go back to our previous example, when we connect the 240 volt supply to a 5 volt electric fan, we basically pump too much electricity into the device in a short period of time and cause it to overheat. Now let's look at the difference between energy and power. Power is defined as the product of current and voltage and is measured in watts, whereas energy is the total power consumption over a period of time. So if we use 200 watt power over 10 seconds, we will consume 2000 joule energy. Also, since the power is calculated as current times the voltage, and the product of current and time is the charge, we can calculate the energy consumption by multiplying the charge and the voltage as shown here. It's just a different way to calculate the energy consumption. Now you know what voltage and current are, we can look at different types of power supply. In general, there are two main types, voltage source and current source, and their electric symbols are shown here. The voltage source will pump out whatever current it needs to maintain its voltage, and the current source will supply whatever voltage it needs to maintain its current. So if we look back to this example, because we have a 240 volt voltage source, it will supply whatever current it needs to maintain this voltage, and the current will depend on the loads itself. Voltage source can be further categorized into AC, alternating current, and DC, direct current. Ideally, from a DC current such as a battery, a fixed voltage will be supplied. But from an AC source, for instance a generator, the voltage and current will alternate. And the 240 volts that we talked about before is in fact the RMS value for this alternating voltage. We use this RMS value to estimate things like the average energy consumption, since the power is also varying at every point in time. Just for your reference, the RMS value can be calculated like this, but in a sinusoidal case, the RMS value is simply the peak value divided by √2. In the next video, we will look at how these basic electric components behave to different power supplies that we just talked about. Welcome back to Introduction to Electrical Engineering. In this optional lecture, we're going to cover more details about electric fields, charges, and electric potentials. By now, you should have a pretty good understanding of what voltage, current, charge, and power are. And in fact, that's really all you need to know for this introductory course to analyze simple DC and AC circuits. But for those of you who want to learn more, I'll talk about the physics behind it in this lecture. To begin with, let's consider a case where we place a point charge in the middle of this sheet. Then, we're going to put 3 metal plates nearby this point charge. By doing so, the electrons which are free to move on the metal plates will actually move towards the point charge, causing one side to be slightly negative and the other to be slightly positive. The movements of the electrons are caused by the electric potential this point charge generated. The electric potential V is not constant everywhere on this sheet. In fact, it depends on the distance from the point charge. For example, the electric potential will be different from point P1 to point P2. Closer to the point charge, higher the electric potential. That's why we write V bracket R, meaning V is a function of the distance R. The actual function can be determined using Coulomb's law for a simple point charge like this, but the function itself is not our focus here. What's important is for you to truly understand what electric potential means. The electric potential has a unit of energy per unit charge. This means if you put a 1 Coulomb charge in the vicinity, this electric potential function tells you how much potential energy this 1 Coulomb charge has. Potential energy by definition is the energy required to bring this charge from infinity to this location. But for now, you can just think of it as a stored energy which can later be transformed into other energy forms such as motion or heat. Note that when we talk about electric potential, we always talk about electric potential difference. This is because the only reference point we know is the electric potential at infinity, which we defined as 0. But it makes no sense to compare the electric potential to an infinite far location, so we use potential difference. Another way to demonstrate this invisible force that pushes the electrons on the metal plate is through electric fields. Electric field lines go from a higher potential to a lower potential. So whenever you have a potential difference, there will be electric fields. Electric fields have a unit of force per unit charge. So it tells you how much force a 1 Coulomb charge will experience if you place it in this electric field. Now going back to our point charge example, here's an illustration of the electric fields generated by the point charge. It's worth noting that inside a perfect conductor, the electric field is always 0. This is because electrons are free to move in a conductor, so if there's any electric fields, like in this case, the electrons will move until the net electric field is zero. Here in this example, you see the electric fields caused by the free moving electrons cancel out the electric fields generated by the point charge, so there's no net electric fields. Since there's no electric fields inside a perfect conductor, we know that there's no potential difference. In other words, the electric potential is constant on a conductor. So looking back to our lecture 3, you can now see why the voltage or the electric potential is the same on the same branch of wires. But I still like my water pump example better. So all of that was just for a simple stationary point charge. What happens when you have a plate of electrical charges? How about a moving point charge? How do you analyze this? When you have moving charges, the magnetic fields are also induced, and this is when we need to use Maxwell equations to determine the electric and magnetic fields. As you can see, this topic is very broad, and it doesn't really help you learn how to use basic resistors, capacitors, inductors, or how to analyze AC and DC circuits. And that's why I'm planning to cover this in the future when we talk about electromagnetic interference. But for those of you who are interested in more details, I hope this additional lecture gave you a better understanding of electric fields and electric potentials. Welcome back to Introduction to Electrical Engineering. Today we're going to look at how resistors, inductors, and capacitors behave to a DC power supply. We're also going to revise on our calculation of energy consumption using a real example. Ohm's law is one of the most fundamental equations in electrical engineering. It basically tells you the relationship between voltage and current for a resistor. According to Ohm's law, the voltage across a resistor is equals to the current flowing through the resistor times the resistance. For example, if we have 5 volt across a 100 ohm resistor, we know the current flowing through that resistor will be 5 divided by 100, which is 0.05 amps. As for a capacitor, the current is equals to the change in voltage times the capacitance. Since a DC supply has a fixed voltage, the current flowing through that capacitor will be 0. In other words, the capacitor will look like an open circuit. Similarly, the voltage across the inductor is equals to the inductance times the change in current. Again, since the DC source supplies a constant current, the voltage across the inductor in this case will be 0. Meaning the inductor will look like a short circuit. So if we have a circuit that looks like this with a DC supply, in a steady state, this is what it will look like. But how does this occur? Looking at the capacitor example, if we now introduce a switch to the circuit, at the instant when the switch is closed, the current starts to flow into the capacitor, and the two metal plates get equal but opposite charges, which leads to a potential difference Vc. As the current continues to flow, Vc increases until it's equal to the power supply voltage. At this point in time, the capacitor is fully charged, and no more currents will flow in the circuit. Now when we open up the switch, if there is a resistor for the capacitor to send power to, it will start to discharge and the voltage across the capacitor will begin to drop. Note that during the whole process, the capacitor only stores and releases energy, but it does not dissipate power. The charging and discharging process is similar in an inductor, but instead of storing energy in the form of electric fields like the capacitors, the inductor stores energy in the form of magnetic fields. As a consequence, the current in the inductor increases during the transient, remains constant in a steady state, and decreases when the energy is released. Therefore, if we have a DC circuit that looks like this, in the steady state, the capacitor will be open circuit and the inductor will be short circuit. And the overall current will just be voltage divided by the resistance, in this case 25 milliamp. And the power consumption is just the product of voltage and current, which is 0.125 watt. So in summary, in a DC circuit steady state, the resistor will follow Ohm's law, whereas the inductor will be short circuit and the capacitor will be open circuit. Now we're gonna look back to what we learned in the last lecture with a practical example, so you're more familiar with power and energy calculations. Assume that we have a 2000 watt oil heater. We use the heater in average 6 hours a day, and it costs 23 cents per kilowatt hour. We want to know that in 3 months, how much will the electricity cost from the use of this heater. So for the 2000 watt oil heater, in each day we will use 2000 watt times the 6 hours in seconds, which is more than 43 million joules, or equivalently 2 kilowatt times 6 hour is 12 kilowatt hour each day. Now in 3 months, we need to multiply that by 90 days, which gives us 1080 kilowatt hour. We know each kilowatt hour costs 23 cents, so 1080 kilowatt hour will cost us $248.40. So now you can go around your house looking at the power consumption of your fridge, your oven, your air conditioner, and figure it out why the cost of electricity is so high. Welcome back to Introduction to Electrical Engineering. In this optional lecture, we're going to go through some common scientific notations that we use in electrical engineering, such as milli, kilo, micro, and pico. We're also going to explain how XY plots should be interpreted. If you already know all of this, feel free to skip this lecture and continue to lecture 5. So, in electrical engineering, measurements can go as large as 10 to the power 12 or as small as 10 to the power minus 12. Instead of writing all these zeros out, we often use prefixes. Here's a list of commonly used prefixes in electrical engineering. You might have seen kilo in kilogram, mega in megabytes, and giga, tera, milli, micro, nano, and pico. Know that they are in the multiple of 1000, and as you start to learn and practice more, you'll get familiar with them, so you don't really have to force yourself to remember them. Now let's look back to lecture 4. You see we used 12 kilowatt hour to represent 12,000 watt hour, and using prefixes we can rewrite this large number as 43.2 megajoules. You will see the use of prefixes a lot in electrical engineering, such as 11 kV power supply, 22 milliamp current, 18 picofarad capacitors, 4.3 gigawatt power, or 120 microhenry inductors. Like I said, you don't have to remember them. You can just go to Wikipedia and find the prefix table and look them up when you need it. What's important is you understand that each prefix represents a number. Now moving on to the XY plot, in electrical engineering, we also use a lot of them. It's a really good way to demonstrate a relationship between two variables. For example, in this graph, we can show how voltage and current are related in a resistive load. In general, in an XY plot, there are 4 quadrants, and the middle point represents the origin 0, 0. The numbers on the right and the upper side of the origins are greater than 0. Therefore, in the first quadrant, x, y's are both positive. In the second quadrant, x is negative and y is positive. Similarly, you can work out the third and the fourth quadrant. Sometimes, if we only care about the behavior in the first quadrant, we'll draw the graph in this way. Or, if the voltage oscillates between positive and negative value over time, we can draw the graph like this, using only the first and fourth quadrant. If you are not familiar with these plots, the best way to interpret them is to give it a few points. Let's take our oscillating voltage example. If we now take 3 points, t equals to 0.1, 0.2, and 0.3, we can find the corresponding voltage. As you can see, the voltage value first increases from 0.1 to 0.2, then it drops to a negative value at 0.3, so we know that this oscillates over time. Now, let's look at another graph that we use in lecture 7 when we talk about diodes. So again, to interpret this graph, we'll take few points. 1, 2, 3, and 4. So from point 1 to point 2, when the voltage is positive, as you can see, we only increase a little bit of the voltage, but there's a dramatic increase in the current. When we continue to increase this voltage, the current will just boost to a very large value, limiting the voltage from further going up. Now, when the voltage is negative at point 3, when we apply a very large negative voltage, there's only a tiny leakage current. As we continue to increase this negative voltage, at some point, it will produce a lot of negative current, and that's what point 4 tells us. So that pretty much summarizes this graph here. I hope now you can all interpret XY graphs pretty easily. Remember, if you ever encounter a problem interpreting these graphs, just put a few points like we did here, and try to explain to yourself what these points tell you. If you still have problems, feel free to email me your graph and I'll explain to you using similar ways. Welcome back to Introduction to Electrical Engineering. In the next 2 lectures, you're gonna learn some techniques to help you analyze a DC circuit. In fact, Kirchhoff current law, Kirchhoff voltage law, nodal analysis, and mesh analysis can all be applied to an AC circuit. But to simplify, I'm just gonna show you a DC circuit example so you know how to use it. We'll come back to AC circuit analysis in lecture 9. Kirchhoff current law tells you that the sum of current flowing into a node equals to the sum of current flowing out of the same node. In this case, we have I1 and I2 flowing into node A, I3 and I4 flowing out of the same node A. So according to Kirchhoff current law, we know that I1 plus I2 equals to I3 plus I4. Kirchhoff voltage law tells you that the sum of all voltages around a loop is 0. To use Kirchhoff voltage law properly, we need to first determine the polarity of the resistors. The polarity of the resistors will depend on how you define the current flow. In this case, if we assume the current flows from the left to the right, like this, because we know that current flows from a higher potential to a lower potential, we will have plus here, negative here, from higher potential to a lower potential, plus here, minus here, plus here. and minus here. So now if we use Kirchhoff voltage law to the outermost loop, this one here, in the clockwise direction, like this, we will have plus Vs, because we go from negative to positive, we have plus Vs, and we go from positive to negative, we have minus V3 and minus V4 equals to 0. Notice that if we go in the opposite direction of the same loop, we will have minus Vs plus V4 plus V3 equals to 0. And these two equations are just the same, because if you multiply this one by minus 1, you will just get that one. Now try to apply Kirchhoff voltage law to the two inner loops and see if you can get these two equations. So this loop and this loop. It's important to know that it doesn't matter which direction you choose your current to flow at the beginning. If you end up having a negative number, it just means that your current actually flows in the opposite direction. So if we assume a current flows this way and we have minus 1 amp here, it just means that minus 1 amp is flowing in this direction, opposite to our initial assumption. Nodal analysis is probably the most straightforward method you can use to solve a circuit. It uses Kirchhoff current law and Ohm's law to give us a system of equations that we can solve using linear algebra. The best way to understand how to use nodal analysis is through an example. So consider a circuit like this. To use nodal analysis, you first need to write down all the voltages and currents that you already know. So in this case, we know VD, VE, and VF are 0 volt because they are connected to a ground which is always 0 volt, and VA equals to VF plus VS, which is 18 volt. Next, we're gonna write down all the currents through the resistors in terms of voltages using Ohm's law. So in this case, I1 equals to VA minus VB divided by R1, I2 equals to VB minus VE divided by R2, I3 equals to VB minus VC divided by R3, and I4 equals to VC minus VD divided by R4. Because from step 1 we already know what VD, VE, VF, and V8 are, and we also given all the resistance, we can sub in the values. Now we have 4 equations. To solve these 4 equations, we just need to relate I1, I2, I3, and I4. And this is when Kirchhoff current law comes in handy. So next we use Kirchhoff current law. At node B, we know that I1 equals to I2 plus I3, and at node C we know that I3 equals to I4. So if we sub in I1, I2, I3, and I4 using the results from the last step, so we sub in I1 here, I2 here, I3 here, I3 here, and I4 here, we'll end up with 2 equations and 2 unknowns, VB and VC. So now you can solve these systems of equations using a computer or by hand. Once you solve VB and VC, you can use Ohm's law to find the rest of the unknowns. For example, I4 is just VC minus 0 volt divided by R4. Since we already solved VC, we know what I4 is. Similarly, I3 is VB minus VC divided by R3, and we already know VB and VC, so we know what I3 is. So we can solve all the unknowns. For the first time, I would recommend you to go through this example yourself and try to solve the system of equations by hand. This should give you a pretty good understanding of how to use nodal analysis. Mesh analysis is just another method you can use to solve the same circuit. Personally, I don't like to use mesh analysis because I think it's a little bit too tedious, but you might prefer this method, and if you are interested, here's how to use it. To begin with, you need to define mesh current so that every branch has at least one mesh current. So here we define Ix and Iy. Next, we need to write down all the currents that we already know. But in this case, since we don't have a current source, we don't know any currents yet at this point. Then we're gonna write down Kirchhoff voltage law for each loop using the mesh currents that we define. So in this case, we have Vs minus I1 times R1 minus I2 times R2 equals to 0. Now we have to replace I1 and I2 with the mesh currents that we define. So in this case, I1 is just equals to Ix. As for I2, because Ix is going downward and Iy is going upward, so I2 is here in the middle, I2. So we know that I2 equals to Ix minus Iy. So the equations now become like this. Similarly, when we go around the other loop, we have plus, because we go from a negative to a positive, so we have plus I2 times R2 minus I3 times R3 minus I4 times R4 equals to 0. It's this one here. Again, we'll sub in our mesh currents and all the values that we know, so we get these two equations. So this is when we sub in our mesh current, and when we sub in the actual values, we get these two equations, equation 1, equation 2. Notice that we have two equations and two unknowns, Ix and Iy, so we can solve it using linear algebra. I'm not gonna go through the details here because I don't want you to get trapped in all the numbers. The important things are the steps and how to use nodal and mesh analysis for different circuits. Once you solve Ix and Iy, you can just find all the branch currents I1, I2, I3 and I4. Now from the branch current I1, I2, I3 and I4, you can use Ohm's law to find out all the voltages. For example, Vc is just 0 volt plus I4 times R4 and etc. But in practice, sometimes you just need to find out one particular current, and when the system gets too large, solving a system of 50 equations with 50 unknowns can take just too much time. So in the next lecture, we're going to teach you some techniques that you can use to simplify a circuit. Welcome back to Introduction to Electrical Engineering. In the last lecture, you learned how to use nodal and mesh analysis. Today we're going to teach you some basic techniques to simplify a circuit. First, we're going to look at resistors in series, and our goal is to simplify this with just a single resistor. So when we have two resistors R1 and R2, each has a voltage drop V1 and V2, we know that the total voltage drop V3 is just V1 plus V2. According to Ohm's law, V1 is just I times R1 and V2 is just I times R2. So when we sub in V1 and V2 in here, we get V3 equals to I times R1 plus I times R2. Now if we take the common factor I out, we end up with this equation. If you look closely, you'll see that we now have another equation in the form of V equals to IR, where V equals to V3, the total voltage drop. R is just the sum of the resistance R1 plus R2, and the current I remains the same. In other words, when you see two resistors in series, you can replace this by a single resistor, and its resistance will be equal to the sum of the two resistors. In fact, this applies to any number of resistors in series. Now, with the same example, let's look at each voltage V1 and V2 in terms of the total voltage V3. We know V1 is just I times R1, and V3 is just I times R1 plus R2. Now if we want to write V1 in terms of V3, we need to eliminate I. So we rearrange this to get I equals to V3 divided by R1 plus R2. Now when we sub in I in here, we get V1 equals to V3 times R1 divided by R1 plus R2. Similarly, we can find V2 by subtracting V3 by V1, and this is what we get. V2 equals to V3 times R2 divided by R1 plus R2. Notice that the ratio of V1 to V2 is R1 to R2. You'll see why this is important with the next example. So now assume we have 4 ohm resistors in here and 5 ohm resistors here, and we supply 9 volt across the whole thing. Using the equation that we just found, V1 equals to V3 times R1 divided by R1 plus R2, we can see that V1 will be equals to 4 volt and V2 will be 5 volt. In other words, using resistors in series with the right ratio, you can divide this voltage up to whatever is required for your circuit. For instance, if we put a 300 ohm resistor here, 600 ohm resistor in here, you will have 3 volts in here and 6 volts in here. And this is why resistors in series are called voltage divider. The mathematical derivation that we just went through is not as important. It's just for those who are interested. What I want you to remember is that first, you can use resistors in series as a voltage divider. Second, you can simplify resistors in series by adding up all the resistance. Next, we're going to look at resistors in parallel, also known as the current divider. Again, if you are not interested in the mathematical derivation, you can just jump straight to the conclusion. For those who are interested, here's how it goes. Our goal is again to simplify this with a single resistor. So we need to find an equation in the form of V equals to IR that represents the whole thing like before. First, we know that V1 equals to V2 because the two terminals of the resistors are connected to the same branch of wires. We talked about this in lecture 3, slide 6. If you don't remember why this is the case, please go back to that slide. Now with Kirchhoff's current law, we know that the total current I is just I1 plus I2, and I1 is V1 divided by R1, I2 is V2 divided by R2. This is Ohm's law. And since V1 equals to V2, we can take the common factor V1 out. So we have I equals to this whole thing times V1. Now if we put this whole thing on the other side, we end up with V1 equals to 1 over R1 plus 1 over R2 times I. Again, this is just in the form of V equals to IR, where V is V1 and R is 1 over R1 plus 1 over R2. So we can use this new resistance to represent two resistors in parallel, and the voltage across it will just be V1. Now with the same example, let's look at each current I1 and I2 in terms of the total current I. Since V1 equals to V2, and V1 is just I1 R1, V2 is just I2 R2, we can write I1 in terms of I2 like this. And because we know that the total current is I1 plus I2, if we substitute I1 here using this, so if we substitute this equation into here, we'll get I equals to this. Now if we take out the common factor I2, we'll end up with I equals to this whole thing times I2. And because we want to write I2 in terms of I, we'll take this whole thing on the other side. And we'll get I2 equals to R1 divided by R1 plus R2 times I. Similarly, we can find I1 by subtracting the total current I from I2, and this is what we'll get. Notice that the total current, the ratio of the current I1 and I2 is just R2 to R1. So now if we supply a 4A current and we use a 5 ohm resistor in parallel with a 15 ohm resistor, using the equation that we just found, we know that I2 is 1 amp and I1 is 3 amp. In other words, resistors in parallel can be used as a current divider. With the right ratio in resistance, you can control how much current flow in each resistor. Next, we're going to talk about another technique you can use to simplify a circuit. Thevenin equivalent circuit tells you that we can find an equivalent voltage in series with an equivalent resistance to represent any linear electrical network with some power source. The best way to learn how to find a Thevenin equivalent circuit is through an example. Assume we have a circuit like this, and we want to find the Thevenin equivalent circuit of this part. The first step is to find the open circuit voltage VOC. So we open up these two terminals and we want to find the voltage across it. If you look at this circuit, this is in fact a simple case of the voltage divider that we just talked about. So the voltage across R2 is just the total voltage Vs times R2 divided by R1 plus R2, which is 4 volt. Thevenin tells us that this open circuit voltage will be the Thevenin equivalent voltage Vt. Next, we need to find the short circuit current ISC. So when we are shorting these two terminals, R2 is bypassed, meaning no current will flow through R2. You can verify this using the parallel resistance equation. So now the circuit becomes like this. ISC is just Vs divided by R1, which is 1 amp. Lastly, the Thevenin equivalent resistance is defined as the open circuit voltage divided by the short circuit current, which is 4 divided by 1, and it's just 4 ohms. So now we know that we can replace this part of the circuit with the Thevenin equivalent voltage of 4 volts in series with the Thevenin equivalent resistance of 4 ohm. This is how you find the Thevenin equivalent circuit, and we can do this with any linear electrical circuit. Welcome back to Introduction to Electrical Engineering. In this additional lecture, we'll go through more examples of the DC circuit analysis so that you're more familiar with the Ohm's law, Kirchhoff current law, Kirchhoff voltage law, nodal and mesh analysis, because they are the most important techniques that you need to master in this course. For anything else, such as the capacitors, inductors, diodes, and etc., we're just giving you an introduction so that you know they exist and just roughly how they work. But you'll learn them in much greater detail in later courses when we need to use them. Now let's focus on the most important topics in this entire course by going through some examples. In this first example, we have two loops, two resistors, and two power sources. So intuitively, we can apply mesh analysis by assuming the loop current, Ix and Iy. And this automatically gives us two unknowns to solve, which is mathematically quite simple. So let's try the mesh analysis strategy. Our assumed loop current, Ix, already defines all the current in these blue branches, while Iy includes all the currents in the yellow branches. So the only current that's yet to be defined is the one in the middle. Let's assume this current, I middle, flows downwards. Based on this assumption, we know that I middle equals to Ix minus Iy. Because Ix is downwards and Iy is upwards on this middle branch. Since we now have every branch current in terms of Ix and Iy and their directions, we know which nodes have higher potential and which nodes have lower potential. Here we'll use plus and minus to indicate them. Therefore, because the current flows from a higher potential to a lower potential, we have plus here, plus here, and minus here. These signs are based on the flow of the directions we assumed, and they are crucial when we apply Kirchhoff's voltage law. Next, we can apply Kirchhoff's voltage law to solve for Ix and Iy. First, let's go clockwise on this left inner loop, starting from this point. We first encounter a voltage source from minus to plus, so we gain a voltage of plus 12 volts. Then we go from a plus to minus, so a voltage drop of 20 times Ix. This is Ohm's law, voltage equals to the current times the resistance. Then we encounter another voltage drop of I mid, which is Ix minus Iy, times 40 ohms. And this should be equals to 0 based on Kirchhoff's voltage law because we have completed a loop. We have two unknowns and one equation so far, so we need another equation. Can we apply Kirchhoff's voltage law on this right inner loop? Do we know what the voltage is across the current source? Remember that we said the current source will supply whatever voltage that it needs to maintain the current. So the voltage across the current source varies. But what we know is that the current source will make sure that this branch current has 2 amp. In other words, Iy equals to 2 amp. Subbing this information back into the first equation, we have plus 12 minus 20 Ix minus 40 Ix minus 2 equals to 0. Now we can expand the bracket, so plus 12 minus 20 Ix minus 40 Ix plus 80 equals to 0. Putting Ix to the right and everything else to the left, we have 92 equals to 60 Ix. So Ix is 1.533 amp. I mid is Ix minus Iy, which is 1.53 minus 2, and that equals to minus 0.46 amp. And hence we know the current in the middle branch is 0.46 amps, and it flows in the opposite direction to what we initially assumed. Now we have every information, we can calculate V1. So V1 equals to 12 volts minus the voltage drop across the 20 ohm resistor, and that is 20 times 1.53 amp. So that gives us minus 18.6 volts, and that's our answer. We can check this answer by applying Ohm's law on this middle branch. Let's see if we can get the same I-mid current by applying Ohm's law using the V1 voltage that we just determined. So minus 18.6 minus 0 divided by 40 should be equals to I-mid, and it is. So our answer is correct and consistent. Now I want you to think about what will happen if we insert an additional 5 ohm resistor here. Try to analyze this circuit again and see what differences it makes. Is V1 different? In this second example, because we have 3 loops here, so if we use the mesh analysis, we'll start with Ix, Iy, and Iz, 3 unknown variables, and that's a lot of unknowns to deal with. So in this case, perhaps the mesh analysis is not a good idea. It starts with too many unknown variables. From experience, I can easily see that these 3 resistors are in parallel, so we can use the parallel equations to combine them into a single resistor, and the whole circuit analysis becomes fairly simple. But let's assume that we cannot tell which ones are in parallel and which ones are in series, so we have to use the fundamental nodal analysis to solve this. First, we need to write the known and unknown voltages. So all these points are 0 volts because they are directly connected to the ground. Then we have an increase of 17.5 volts. We don't know the voltages at these points, so let's call them V1, V2, and V3. And because V1, V2, and V3 are connected with a wire, there's no voltage drop between them. So V1 equals to V2 equals to V3. We can just use one variable to represent the voltage of these 3 points. Now at this first point, if we assume the current flows in these directions, we know that the current flowing in, so 17.5 minus V1 divided by 5 equals to the current flowing out. So V1 divided by 10 plus I1. I1 is the pink current, which we don't know its value yet. Then we'll apply Kirchhoff's current law again at this second junction. Again, we need to assume the directions of the current, and this defines how we subtract our voltages in the Ohm's law. Then we can say the current flowing in, so I1 equals to the current flowing out. So V1 divided by 5 plus V1 divided by 5. Now we know what this I1 is, we can substitute back into our first equation. But before we solve this, I just want to quickly show you why it doesn't matter which directions you assume the currents to flow, as long as it's consistent when you apply the Ohm's law. Let's focus on this second junction again. If now I assume the current flows in these directions, again we'll have the current flowing in, so I1 plus I yellow equals to the current flowing out, I orange. And I yellow equals to 0 minus V1 divided by 5 ohms, because the current flows from a higher potential to a lower potential. Our new assumption of the current directions tells us the 0 volt is the higher potential. So the final equations becomes I1 minus V1 divided by 5 equals to V1 divided by 5. And as you can see, they give us the same equation. So it doesn't matter which directions you assume the currents flow, as long as when you apply the Ohm's law and the Kirchhoff current law, you're consistent with the directions you assumed. So back to our example, subbing I1 into here, we have 17.5 minus V1 divided by 5 equals to V1 divided by 10 plus V1 divided by 5 plus V1 divided by 5. There are many ways to solve this, but I don't like to deal with fractions, so let's multiply both sides by 10. On the left, we have 2 times 17.5, which is 35 minus 2V1 equals to V1 plus 2V1 plus 2V1. Now we can put everything with V1 on the right. So V1 plus 2V1 plus 2V1 plus 2V1 is 7V1 equals to 35. And therefore V1 equals to 5 volts. Now we have the value for V1, we can find out all the branch currents using the Ohm's law. I'll leave that for you to practice and finish. Next, I want you to pause the video and try to solve this very similar circuit using whatever methods that you're comfortable with. But before you start, I want you to think about which resistors are in parallel and which resistors are in series and why. Because simplifying a circuit before applying mesh or nodal analysis can make your math equation much simpler, and it's much easier to solve. Once you solve all the voltages and all the branch currents, unpause the video, we'll reveal the answer in 5 seconds. Okay, here is the answer. Regardless of whether you got them right, you're certainly more familiar with all these important techniques. If you have any question, feel free to post them on the discussion forum, because like we said, the Ohm's law, the Kirchhoff current law, Kirchhoff voltage law, mesh analysis, and the nodal analysis are the most important techniques for this first year introductory course. You'll be using them throughout your entire electrical engineering journey. If you can apply them correctly and consistently, you're pretty much ready for the next level electrical engineering course, because for everything else, like the capacitors, transistors, diodes, and etc., we'll come back to them in more details when we need to use them. Welcome back to Introduction to Electrical Engineering. Today we're going to introduce you to commonly used active circuit elements, the diodes and bipolar junction transistors. Diodes are made by joining a p-type semiconducting layer such as boron to an n-type semiconducting layer like phosphorus. This particular layout allows the diode to conduct current in only one direction. Diodes has 2 terminals, an anode and a cathode. The side where the p-type semiconducting layer is placed is called anode, and the other side is called cathode. When the voltage on the anode is higher than the voltage on the cathode, the diode is said to be forward biased, and this is when the diode conducts current. If the voltage on the cathode is higher, the diode is reverse biased, and only a very small leakage current will flow under this mode. This graph shows the characteristic of a diode. For a silicon diode, a typical forward voltage is 0.7 volts, meaning that if the diode is forward biased and the voltage across the diode is greater than 0.7 volts, the voltage will be capped at 0.7 volts and the diode acts like a short circuit. In a reverse bias region, unless the reverse voltage is greater than the breakdown voltage, the diode acts like an open circuit with a very small leakage current flowing through it. With this characteristic, diodes are sometimes used as a voltage limiter. Consider a circuit with a sinusoidal output. If we place a diode in this direction, when the voltage enters the positive cycle, the diodes will conduct current and limit the voltage by its forward voltage. In the negative cycle, the diode is reverse biased, so it acts like an open circuit and the output voltage will just remain the same. If we now place two diodes back to back like this, we can limit both positive and negative voltages. More commonly, diodes are used as a rectifier. When we place the diodes in series with the AC supply, in a positive cycle, the diode is forward biased, so it will allow currents to flow to the load. In a negative cycle, the diode is reverse biased, so no significant currents will be flowing into the load. This allows us to remove the negative part of the supply, which is why it's called a rectifier. Another commonly used diodes are LEDs, light emitting diodes. It emits light when activated. LEDs use less energy and have a longer lifetime, which is why they're used almost everywhere. Next, we're going to look at bipolar junction transistors, BJT. Bipolar junction transistors have three terminals: a collector, a base, and an emitter, and they are manufactured in two types, NPN and PNP. In an electrical circuit, we often draw an NPN transistor like this and a PNP transistor like this. The basic function of a BJT is to amplify current. This is when the transistor is in the forward active mode. Take a NPN transistor as an example. The transistor operates in the forward active region when the voltage at the collector is greater than the voltage at the base and greater than the voltage at the emitter. In this mode, the collector current is about 200 times the base current, and the emitter current is almost equal to the collector current. Now, if the emitter voltage is greater than the base voltage and greater than the collector voltage, the transistor is in the reverse active mode. Reverse active mode is similar to forward active mode but with a smaller current gain. The NPN transistor can also operate in cutoff and saturation mode. In the saturation mode, the base voltage has to be larger than both the collector and emitter voltage, and in this mode, the current flows from the collector to emitter like a short circuit with only a very small voltage drop of less than 0.2 volts. Whereas in the cutoff mode, the base voltage is smaller than both the emitter and collector voltage, and no current will flow from the collector to emitter. The PNP transistor also operates in 4 different modes, and the function in each mode is exactly the same as NPN transistors. The only difference being that the emitter and collector have now swapped their positions. For example, to operate in forward active mode, you'll need to have emitter voltage greater than the base voltage greater than the collector voltage. However, in this mode, the transistor still acts like a current amplifier. Here's an example of using an NPN transistor as a dark activated switch. When the photoresistor is exposed to light, its resistance drops, causing most of the current to go from the supply through resistor R1 to the photoresistor. Only a very small fraction of current is flowing to the base of the transistor, which is not enough to turn on the transistor. Therefore, no current will flow through the collector-emitter junctions, and the LED will not light on. In the dark, the resistance of the photoresistor starts to increase dramatically, causing most of the current to flow to the base of the transistor, which turns on the transistor. As a result, the current will flow through the resistor R2 and LEDs to the collector emitter junction, so the LEDs will now light on. Another commonly used applications for transistors is to use them as Darlington pair. In the Darlington pair, the transistors are connected in such way that the current amplified by the first transistor is further amplified by the second transistor. So the total current gain is much higher than each transistor taken separately. If you look at the schematic of an operational amplifier, which we're going to talk about in the next lecture, you'll see Darlington pair being used for high current gain. Welcome back to Introduction to Electrical Engineering. Today we're going to continue to look at some commonly used active circuit elements. In particular, we're going to learn how operational amplifiers work and how we can use them. This is the internal schematic diagram for the operational amplifier UN741. But to understand how it works, we're going to look at the equivalent circuit. An operational amplifier, also known as an op-amp, usually has two inputs and one output, and it requires some power supply. The output voltage of an op-amp is the difference between the two inputs multiplied by a very large gain, usually in an order of 100,000. This is why op-amps are sometimes used as a comparator to compare the two input voltages. Op-amp has a very large input resistance and a very small output resistance. Therefore, we can assume that no current is flowing into the two input terminals, and the voltage drop across the output resistor is insignificant. Although we know the output of an op-amp has this relationship, if we input a 5-volt difference to this op-amp, we still cannot achieve the 500,000 volts at the output, like what the equation tells us. This is because the output voltage of an op-amp is kept by its power supply, VCC. In this example, we cannot even achieve negative voltages at the output because of the power supply. So to use an op-amp, first you'll need a proper power supply. Second, you usually have some sort of negative feedback. Let's look at a non-inverting amplifier as an example. To see how this circuit works, assume we start by inputting a voltage, say 3 volts at Vin. Initially, the voltage at V- is 0 volt, so the output voltage will take the difference between the two inputs and start to increase. As Vout increases, V- will also increase because no current flows into the negative terminal. So this part of the circuit will just look like a voltage divider, where V- equals to Rg over Rg plus Rf times Vout. Now, since V- has increased, the difference between the two inputs decrease. Therefore, Vout will decrease. Eventually, Vout will stop fluctuating, and we call this the steady state. At steady state, the output voltage Vout doesn't change, and therefore the two input voltages V plus and V minus are the same. In fact, we can use this conclusion to analyze any op-amp circuit with negative feedback. We now know what negative feedback does. We can continue with this example. So at the steady state, V plus equals to V minus, which is also equals to V in this case. We also know that V minus equals to this times V out. So if we sub in V in equals to V minus in here, we'll get V in equals to this times V out. Now if we rearrange this, we know that V out equals to Rg plus Rf over Rg times V in. In other words, if we put a kilo ohm resistor in Rg and Rf, we'll get V out equals to 2 times V in. So the output voltage will be twice the input voltage, which is why we can use this as a voltage amplifier. Now let's analyze another op-amp circuit with negative feedback. Again, we know that at steady state, V plus equals to V minus, which is 0 volt in this case. So if we look at this part of the circuit, it will just become like this. Now with Kirchhoff's current law, we know that the current flowing through this resistor will be equals to the current flowing through this resistor. So V in minus 0 divided by R in equals to 0 minus V out divided by RF. Now if we rearrange and simplify this, we know that V out equals to minus RF divided by R in times V in. Again, if we put in a kilo ohm resistor in RF and R in, we know that V out equals to minus V in. So if we have an input like this, the output will just look like this. And this is why this amplifier is called inverting amplifier. Another very interesting but commonly used configuration for the operational amplifier is this. This is known as the voltage follower. Basically, the output voltage will just be the same as the input voltage. So why do we need to use this? Why don't we just have a wire to pass on the input voltage like this? To answer this, you need to understand that op-amp has a very large input resistance and a very small output resistance. So this kind of the circuit is useful when you are trying to separate two circuits. You'll learn more about this in the future when you need it. You can also use op-amp as a summing amplifier to add up several input voltages like this. I would like you to follow the steps and try to analyze this circuit yourself to see if you can get this equation. Lastly, we can use op-amp as a difference amplifier to subtract two voltages. Again, please try to analyze this op-amp circuit, and if you have any questions, please let me know. Welcome back to Introduction to Electrical Engineering. In the last 8 lectures, we learned how to analyze an op-amp circuit with resistors. We also learned the characteristic behavior of the inductors and capacitors. So today and in the next lecture, we're going to slowly guide you to be able to analyze an AC circuit with resistors, capacitors, and inductors. When we talk about AC circuit analysis, most people will just tell you that you need to use impedance instead of resistance. So the Ohm's law, V equals to IR, will just becomes V equals to IZ, where the impedance Z consists of a real number plus an imaginary number. Then they will start to talk about complex number analysis and phases. But what's important is that we need to understand why we use a complex number in the real world and what the imaginary part really represents. Since they are imaginary, do they actually exist? To answer these, let's revise how a capacitor works. Consider this circuit. When we close the first switch, the capacitor starts to charge and the energy is stored in the form of an electric field. Once the capacitor is fully charged, we open up the first switch and close the second. This allows the capacitor to deliver its energy to the resistor. Notice that during this whole process, the capacitor does not dissipate power itself. It only stores and releases energy. So when we talk about energy and power, we need another dimension to describe this behavior, and that's why we use a complex number to represent an AC power. So when we describe power in an AC circuit, we use a real number P to represent the real power that's being dissipated, and an imaginary number Q to represent the reactive power that's never been used. And the apparent power S is just a complex number that consists of these two values. Note that even though the reactive power is not dissipated, the power supply company will still need to deliver this power unnecessarily. Therefore, in practice, as a client, we often need to keep this reactive power as low as possible. In an AC circuit, because of the inductors and capacitors, there will always be a phase shift phi between the voltage and current. Let's compare that to a circuit with only resistors. From this phase shift phi, we can calculate the average real power P and the reactive power Q. By definition, the real power in an AC circuit is equals to the RMS value of the voltage times the RMS value of the current times cos phi, where phi is the phase shift between the voltage and the current, whereas the reactive power Q is defined as the product of the RMS values of the voltage and current times sine minus phi, and the apparent power is just a complex number combining these two values, S equals to P plus JQ. We call this cos phi the power factor. The power factor is important because it will tell us whether a load is inductive or capacitive, so that we can correct this power factor to make it close to a resistive load. Now let's look at what happens when you have a current lagging a voltage. In this case, the phase shift is greater than 0, so the power factor cos phi will also be greater than 0, and we know that we have an inductive load. On the other hand, if you have a current leading a voltage, we know that phi is now negative, so the power factor cos phi is smaller than 0, and we have a capacitive load. Next, we're going to look at a practical example so you know why this power factor is very important. Assume a power supply company provides a 240 volts AC supply, and the client requires 10 kilowatts real power, and the phase shift due to the client's load is 45 degrees. Now the power factor company wants to know what the peak current is that they need to supply that. First, we know that the real power P is equals to Vrms times Irms times cos phi, which is required to be 10 kilowatt. We also know that Vrms is 240 and phi is pi on 4. So we can sub in those values and we get Irms equals to 58.9 amp. So the required peak current is just Irms times root 2, which is 83.3 amp. Now with the same example, let's assume that we have a pure resistive load, so there is no phase shift, phi equals to 0 and cos phi equals to 1. Now we do the same calculation. This time, the required peak current is only 58.9 amp. As you can see, to supply the same amount of real power to the client, because the client's loads are highly inductive, the power supply companies needs to deliver way more current than it actually needs. So usually in practice, the power supply company will require the client to design some sort of power factor correction circuits to make the power factor close to 1. If the power factor is too low, usually a fine will be issued to the client. So when we design our circuit, how do we know what this phase shift phi is without actually having to energizing the circuits and plotting voltage and current? We will learn this in the next lecture. Welcome back to Introduction to Electrical Engineering. In the last lecture, we learned why we use complex numbers in AC circuit analysis. We also learned the importance of the power factor in AC circuits. Today we're going to look at what impedance is. We're also going to show you how to use impedance to determine the phase shift between the voltage and current using a practical example. So previously, in the DC circuit analysis, we learned that the voltage and current follows Ohm's law, V equals to IR, where R is the resistance of the resistor. Now in the AC circuit, we'll use V equals to IZ to represent Ohm's law, where Z is the impedance consisting of the resistance R in the real part and the reactance X in the imaginary part. The reactance X exists because of the capacitors and inductors, and the reactance of a capacitor can be calculated as 1 over j omega c, whereas the reactance of an inductor is given as j times omega times L. This j is the imaginary unit, c and L's are the capacitance and the inductance that we talked about in lecture 2, and omega is the angular frequency in radius per second. Notice that the reactance is frequency dependent, therefore, depending on the input frequency, the capacitors and inductors will behave differently. To use V equals to IZ in the AC circuit analysis, next, we'll need to write down the voltage and current in the phasor form. To do this, you simply write down the amplitude and the phase angle of the voltage and current. Let's look at a bunch of examples. So if you have a sinusoidal voltage with an amplitude of Vm and a phase angle of phi1, in the phasor form, you'll write down V equals to Vm with a phase angle phi1. So in this case, you'll write down V equals to the amplitude 12 and the phase angle 0 degrees. For the current, you'll write down the current in the phasor form using the same way. So in this case, in the phasor form, I will just be the amplitude Im with the phase angle phi2. And in this case, in the phasor form, I will becomes 0.3 with phase angle 60 degrees. And lastly, this will becomes I equals to 0.3 with a phase angle 0.4 radius. So next, let's look at how we can simplify an AC circuit. Similar to DC circuit analysis, in AC circuit, you can simplify series impedance in the same way that you do to series resistance. So when you have impedance in series, just like resistance, you can simply add them up. And the voltage across each of the series impedance can be calculated using the same formula as in the voltage divider case. So V1 will be equals to Z1 divided by Z1 plus Z2 times Vs, and V2 will be equals to Z2 divided by Z1 plus Z2 times Vs. Now when you have impedance in parallel, again you can use the same formula but simply replace the resistance by the impedance as shown here. So the current flowing through the parallel impedance I1 and I2 can be calculated just like the current divider case. So I1 is just Z2 divided by Z1 plus Z2 times Iin, and I2 is just Z1 divided by Z1 plus Z2 times Iin. If you don't remember how we derive these equations, you can go back to lecture 6 where we talked about simplifying DC circuits. It's worth noting that the conductance and admittance are just a reciprocal of resistance and impedance, because you'll sometimes hear engineers use them instead. Now you see we do a lot of additions, multiplications and divisions to impedance, voltage and current, which are all complex numbers. We need to learn the complex number arithmetic. So to change from the polar form, which we use for phasors, to a rectangular form, if we have V equals to Vm with phase angle phi1 in the rectangular form, the real part is simply Vm times cos phi1, and the imaginary part is Vm times sin phi1. Now to convert back to the polar form, if we have impedance Z equals to A plus JB, we know that the amplitude is just the square root of A squared plus B squared, and the phase angle phi is the inverse tangent of B over A. This is just simple trigonometry, and you can see this when you draw them in a complex plane like this. Now to do additions and subtractions, you will use the rectangular form and simply add the real and imaginary parts separately. As for multiplications and divisions, you will use the polar form, multiplying or dividing the amplitude, and add for multiplication or subtract for division the phase angle. You will get familiar with this when you see more examples. Now with what we learned, let's look at this simple RLC circuit. Assume we have a voltage supplied of 50 volts amplitude at 50 Hz. We know that the angular frequency is 2 times pi times f, which is 100 pi radians per second. And assume that we have a 100 ohm resistor in series with a 10 Henry inductor and a 1 microfarad capacitor. How can we determine the current I and the phase shift between the voltage and the current? To do this, first we need to determine the impedance of these three elements. So for the resistor, the impedance Z1 is just 100 ohms. And for the inductor, Z2 is J times omega times L, where omega is the angular frequency and the L is the inductance. So when we sub in the values, we know that Z2 equals to this. Now for the capacitor, the impedance is 1 over J omega C. Again, the omega is the angular frequency and the C is given here. So when we sub in the values, we know that Z3 equals to this. Now since we have Z1, Z2 and Z3 in series, we can simply add the impedance up. So you just add the real part and the imaginary part separately. And you know that the Z total, ZT, equals to 100 minus J times 41.5 ohms. We can convert this to a polar form, which will give us 108.3 with a phase angle of minus 0.39 radians. So now the current is just V divided by Z total, which is 50 with 0 radians divided by 108.3 with minus 0.39 radians. And so when we do this calculation, we know that the current I is 0.46 amp with a phase shift of 0.39 radians. Since the phase angle is positive, from the last lecture, we know that we have a leading current and a capacitive load. Note that both DC and AC circuit analysis allows you to determine the expected voltage and current at any point in the circuit. So when you design and build your own circuit but it fails to function, you can use circuit analysis in combinations with voltmeters, ammeters or multimeters to debug your circuit and find out where the problem is. And that's why we're learning this. Welcome back to Introduction to Electrical Engineering. Because almost all electronic devices need some power source, it's important to understand how power is generated and distributed. So in this lecture, we'll talk about some basic components used in the power system and what their roles are. First, let's look at how a basic generator works. When you place a conducting coil in a magnetic field like this, as the coil rotates, the area perpendicular to the magnetic field changes, and the change in the magnetic flux induces current. This is known as the Faraday's law. So to generate electricity continuously, all we need is a mechanical force that keeps the coil rotating. Different types of power plant use different methods to keep the coil rotating. For example, in the nuclear power plant, The heat is released when the nuclear fission occurs, and this heat is used to boil water and create steam. The steam is then used as the mechanical force to push the turbine to rotate, and that generates electricity. Similarly, in the hydro power plant and the wind power plant, the water and the wind are used to rotate the turbine and generate electricity. Once the electricity is generated, we need to distribute it to the client, and the major power loss can be resulted from the distribution. Consider this: if we use a cable which has a resistance of 70 ohms per kilometer, and we want to deliver 2400 watt power at 240 volts to a client who is 100 km away. Since the power equals the current times the voltage, at 240 volts to deliver 2400 watt power, we know that we need 10 amp current. Now, over 100 km, we know that we will have 70 times 100, which is 7000 ohm resistance from the cable. So the total power loss is P equals to I square R, which is 700 kilowatt. In other words, to deliver 2.4 kilowatt power at 240 volts, we will lose 700 kilowatt power in the distribution, and this is just impractical. Now, if we deliver this power at a higher voltage, we know that we need less current and therefore less power loss. And this is why in a power system, you often see transformers being used to step up the voltage before delivering to the client. The most basic transformers would have a primary winding and one connected to a power source, an iron cord, and a secondary winding and two connected to a load. When a alternating current flows through the primary windings, it induces change in the magnetic field. The change in the magnetic field is then carried via the iron cord to the secondary winding, and this change in the magnetic field then induces current in the secondary winding. In an ideal transformer, the ratio of the voltage on the primary winding to the secondary winding is directly proportional to the turns ratio N1/N2, whereas the ratio of the current on the primary winding to the secondary winding is inversely proportional to this turns ratio. So if we have a transformer with a turns ratio of a half, we know that we can use this transformer to double the voltage and half the current. Ideally, the input power P1 should be the same as the output power P2. And here's how we will draw a transformer in an electrical diagram. To protect all of these equipments from overheating, we often use fuses or nowadays circuit breakers in a power system. The purpose of using fuses and circuit breakers is the same. They monitor the current flow, and if too much current is detected, they'll open up the circuit, preventing any equipment from being damaged. Fuses have a voltage rating and a current rating, and in an electrical diagram, they are drawn like this. To choose the right fuse, you'll need to use the fuse with the same voltage rating as your circuit, and the current rating that is slightly above your maximum load current. So for instance, if you know that your maximum load current is 1 amp, you should choose a fuse that is rated at 1.25 amp to prevent fault. If you choose 0.8 amp, your fuse will blow up even under normal operation. However, if you choose a 30 amp fuse, your device are not protected from an overcurrent of say 20 amp. So now we know how the power system should look like. First, we have the power plant that generates the electricity. Then we step up the voltage using transformers to reduce power distribution loss. The electricity is then carried through transmission lines, and before it's supplied to the client, we use transformers again to reduce the voltage to whatever the client requires. Fuses and circuit breakers are used along this line to protect all of these equipment. Welcome back to Introduction to Electrical Engineering. In this last lecture, we're going to look at some real circuits, and we're also going to show you how you can start designing your own one. This is a simple residential electrical diagram. You should be able to analyze this with everything that we have learned. Now let's look at this together. So the current flows from the positive end on the red cable through a fuse in the main switchboard, then it goes to a meter which records how much electricity you have used. Then it goes to the main switch, which allows you to turn everything off. This power supply is then divided into 4 branches. Each has its own fuse to protect the devices underneath them. So let's say your power outlet has stopped working. From this diagram, you can see that your 30 amp fuse has probably blown up, and there's likely a fault in your remain circuit. Here's another way the household electrical diagram may be drawn. As you can see, in this case, each room has an independent power supply, so if any problem occurs in one room, you can just investigate the circuits in that particular room. Now, to create your circuit, first you need a breadboard. The breadboard has many pins which allows you to easily connect your wires and electronic components. The pins in the top and bottom 2 lines are horizontally connected, and we often use these pins for the power supply and the ground connection. In the middle part, there are 2 sections. In each section, the 5 pins are vertically connected. So let's say if you want to put 2 resistors in series with the power supply, this is one way you can do it. Now, if you want to measure the voltage across the first resistor, you will just need to use 2 wires to make a parallel connection with the first resistor to the voltmeter. Note that you wouldn't connect a resistor like this because essentially you are just connecting the 2 ends of a resistor to a single point. The key to use the breadboard is to keep it neat and the wires color coded. Usually we use the red wires for the power supply and the black and green wires for the ground connection. If you connect your breadboard like this and the output isn't what you expected, it's almost impossible to debug and figure out where the mistake is. Lastly, you should get familiar with reading data sheets. Data sheets will tell you what the pin layout is for a particular device, so you know how to connect it. Besides, you'll see what the power supply you'll need for this device and what limitations this device has. Also, the data sheet will often teach you how you can connect your device for some typical applications. So now follow these steps and try to design your own circuit using resistors, capacitors, inductors, BJT diodes, op-amps, and everything that we have learned. You can always try to learn a new device by reading its data sheet. So be creative and have fun. Congratulations! You have now finished Introduction to Electrical Engineering. This is just an introductory course covering most of the basic knowledge that you will need in electrical engineering. If you are interested, I will continue on teaching more advanced knowledge in electrical engineering, so you know the answers to questions like how does Siri work. Please let me know if you like this course. Thank you.